Welcome, everyone. Let's get started. Today, we are moving beyond simple, single-turn prompts and diving into one of the most powerful workflows in AI, recursive prompting loops. We will explore how to take Claude's output from one stage and feed it directly back into the next, creating autonomous, self-refining engines for your most complex projects. Let's start by defining our core concept, recursive prompting loops. In a standard workflow, you ask Claude a question, it gives you an answer, and the transaction is over. But what happens when you need to write a 50-page technical manual or analyze a massive dataset? A single prompt will fail. This is where recursive loops come in. By definition, a recursive prompting loop takes the output generated by Claude in one stage and automatically feeds it back as the input context for the next stage. We do this because asking an AI to do everything at once overwhelms its reasoning capabilities. Breaking a task into sequential, dependent stages allows for compounding intelligence. You are effectively creating an assembly line. Stage 1 might gather facts. Stage 2 takes those facts and outlines a document. Stage 3 takes that outline and drafts the content. By treating Claude's output as an intermediate state that feeds the next prompt, you unlock the ability to tackle multi-part, enterprise-grade projects. Take a look at this basic pipeline diagram. On the far left, we begin with our initial prompt. This generates output 1. Instead of stopping there, output 1 is pulled into the recursive pipeline node. The system takes that raw output, packages it into a new refinement prompt, and sends it right back to Claude. This second pass generates output 2, which ultimately becomes our high-quality final deliverable. This visualizes the fundamental output becomes input loop. The most practical implementation of a recursive loop is prompt chaining, specifically used for self-correction. When working with Claude, explicit prompt chaining means breaking a task into sequential API calls. This is incredibly useful because you can inspect the intermediate outputs or enforce a rigid pipeline structure. The absolute most common and effective pattern here is the self-correction loop. The process works like this. First, you ask Claude to generate a draft. Then, you take that draft and feed it into a new prompt, asking Claude to review it against strict criteria. Finally, you take both the draft and the critique and ask Claude to refine the work. Because each step is a separate API call, you maintain total control. You can log the intermediate drafts, evaluate the critiques, or branch off into a different workflow if the draft fails a quality check. By separating the generation of ideas from the evaluation of those ideas, you dramatically increase the quality of the final output. This state diagram maps out the self-correction loop. We start in the generation phase, producing a raw draft. That draft flows directly into the critique phase, where Claude acts as a judge. The original draft and the new critique are then pushed into the refinement phase. Notice the evaluation gate at the end. If the refined text still fails our criteria, we recursively loop back to the critique phase. If it passes, we exit successfully. This guarantees quality control. Now let's explore a more advanced technique, the recursive chain of thought. This isn't just asking Claude to think step by step. This is a method that builds layers of analysis that reference and intentionally refine each other. In a standard chain of thought, the model reasons linearly. In a recursive chain, we instruct Claude to evaluate its own previous thoughts. For example, you set up a prompt that dictates multiple levels. Level 1 asks Claude to identify the core issue. Level 2 explicitly forces Claude to question the assumptions it just made in Level 1. Level 3 asks it to synthesize the first two levels into a refined understanding. You can continue this to Level 4 to find patterns, and Level 5 to project second-order effects. This forces Claude to dig far beneath the surface. However, you must build in validation. If Claude makes a logical error in Level 1, that error will aggressively compound as it builds subsequent levels on top of it. Look at how the recursive chain of thought cascades downward. We start at Level 1 with the core issue, which feeds into Level 2 where assumptions are aggressively challenged. Level 3 synthesizes this debate. But notice the critical diamond in the middle, the quality check. Before we allow the loop to proceed to deep pattern recognition in Level 4, we must validate the logic. If it fails, we loop back to Level 1. If it passes, we proceed safely to Level 5. A highly effective subset of recursive thinking is the self-questioning cascade. This technique makes Claude interrogate its own responses by building quality checks directly into the prompt. Normally, you would ask Claude for a solution, read it, find a flaw, and write a second prompt asking Claude to fix it. The self-questioning cascade automates that entire loop. You structure your prompt to say, solve this problem. Then, after your initial solution, ask yourself 3 critical questions about your approach. Answer those questions. Based on those answers, revise your original solution. You are embedding the recursive feedback loop directly into a single massive execution. It forces the model to play devil's advocate against its own logic. As a deep dive tip, always include a fallback instruction in your prompt. Tell Claude, if at any point the reasoning seems circular or the questions become irrelevant, simplify the approach and focus on the core issue. This prevents the AI from getting lost in endless philosophical loops. This sequence diagram shows what happens inside Claude's engine during a self-questioning cascade. The initial prompt goes in, and Claude begins an internal loop. It generates the initial solution, formulates 3 critical questions attacking that solution, answers those questions itself, and then revises the solution based on its own findings. Only after this entire 4-step internal recursive loop completes does it return the final, highly optimized output back to you. Let's level up to meta-prompting loops. This technique focuses on process improvement. Instead of just refining an answer, we are creating feedback loops to systematically refine the conversation process itself. Think of it as the prompt evolution engine. Sometimes, you don't actually know the best questions to ask to solve a complex problem. You start by asking Claude, what are the 5 most important questions I should be asking about this? Answer question number 1. Then, based on that answer, how should we refine questions 2 through 5 to be more targeted? You are recursively updating your roadmap based on real-time discoveries. The output of question 1 literally changes the input prompt for question 2. However, it is vital to understand the reality of meta-prompting. The AI cannot truly optimize on its own. It merely suggests improvements. As the human operator, you must evaluate whether the newly refined questions are actually more useful than the original ones. This diagram maps the prompt evolution engine. We start on the left by drafting 5 initial questions. Claude answers Q1. That answer flows into a meta-evaluation node. Based on the insights gained, Claude actively refines Q2 through Q5 to be more targeted. We then hit a manual gate where the human approves the new prompts. Once approved, Claude answers the newly refined Q2, and the loop continues, getting sharper with every iteration. A massive engineering challenge with recursive prompting loops is context management. When you continuously feed Claude's outputs back as new inputs, the conversation history grows linearly. Every single message and response accumulates in the context window. If left unchecked, an endless recursive loop will quickly hit the maximum token limit. Even before hitting the limit, excessive irrelevant context degrades the model's focus and spikes your API costs. To solve this, you must build a compaction step into your loop. When the context gets heavy, you prompt Claude to generate a structured continuation summary. You then clear the session and start a fresh loop using only that summary as your initial input. A professional continuation summary must include 4 things: the task overview, the current state, important discoveries specifically including approaches that failed so the AI doesn't repeat them, and the specific next steps. This is how you sustain infinite loops. This state diagram visualizes context compaction. As we move from loop iteration 1 through 3, the context grows heavy. Before the system breaks, we hit the compaction trigger. Inside this trigger, the AI summarizes the state, extracts failed attempts so we don't repeat mistakes, and defines next steps. We then flush the memory, spin up a fresh session, and inject that dense summary. The recursive loop safely continues to iteration 4 without token bloat. Let's tie this all together with a powerful real-time use case, the research synthesis engine. Imagine you need an 800-word, highly technical white paper on semiconductor development, fully cited with recent patents. You cannot do this in one prompt. Instead, we deploy a recursive loop architecture. Stage 1 is the research loop. Claude iteratively searches the web and fetches patent APIs. The output of this data dump feeds into Stage 2, the synthesis loop. Here, Claude analyzes the raw data. If it detects the evidence is too thin, it automatically executes a handoff back to the research loop to gather more data. Once sufficient data is confirmed, it passes to Stage 3, the drafting loop. Claude drafts the text, applies our self-correction critique to its own writing, and refines the document. In just a few minutes, this pipeline of interconnected, recursive prompts produces a heavily cited, structurally perfect white paper that would take a human days to compile. This flowchart maps our research synthesis engine. The white paper task enters the Stage 1 research loop to fetch live data. This feeds into the stage 2 synthesis loop, where we hit a critical decision node. Is the data sufficient? If no, we execute a handoff, looping recursively back to stage 1. If yes, we proceed to the stage 3 drafting loop, executing our draft critique refine chain, ultimately outputting the final cited white paper. To wrap up, recursive prompting loops are incredibly powerful, but they require strict guardrails. The biggest danger is error amplification. If your first prompt produces flawed logic, the recursive loop won't fix it, it will build upon it, compounding the error exponentially. To prevent this, you must install human validation gates. Always pause to validate key assumptions after major synthesis rounds before allowing the loop to proceed. Furthermore, learn to recognize stagnation. If Claude's reasoning becomes circular or artificial, break the loop immediately, clear your context, and restart with a simpler approach. Finally, for developers, use JSON structured outputs between your loop stages to guarantee the data is perfectly formatted for the next prompt. Thank you so much for joining this advanced training session. To truly master these AI capabilities and accelerate your career, I invite you to like this video, subscribe to our channel, and visit quicktechie.com. At quicktechie.com, you will find premium certification prep, including massive Q&A banks, full ebooks, audiobooks, full-length training courses, and expert interview guides. See you there. Our final diagram illustrates the ultimate safety mechanism, the human validation gate. Every recursive output must pass through this checkpoint. If you detect flawed logic or circular reasoning, you halt the loop and simplify your prompt. If the logic is verified, you format the data as structured JSON and safely feed it to the next loop stage. And whatever path you take, your final step should be visiting quicktechie.com to continue mastering these advanced workflows.